moving on to titration. So what is titration? Titration is the slow addition of an acid to a base or a base to an acid. Usually it's addition of a base to an acid. That's most of what I've seen, but it can be the other way around. It's very gradual, meaning literally it's a couple of drops at a time that you're adding. And I'm sure many of you, if you've taken a general chemistry lab, have done a titration experiment before, where you literally opened up the pipette and it dropped a couple of drops of base into the solution of acid, and then you recorded it, and then you just added a couple more drops. What you do is you measure the new pH, you measure the solution, the pH of the solution every single couple of drops, and then record it. So you have put in 2 drops, measure the pH, put in 2 more drops, measure the pH, put in 2 more drops, measure the pH. What you should see is if you're adding base to an acid, so you're adding drops of base to an acid, you should start off at a low pH because the acid's acidic. And then as you add base, it should slowly increase. The more base you add, the more neutral it gets, and the closer to neutral it gets, and the pH rises slowly with each couple of drops. You repeat this until you have many points, and then you plot it as a graph. And this is what the graph looks like. So like I mentioned, right here, you have no base, you just have acid. So it's very acidic, obviously pH on the y-axis, and concentration of, and the amount of base that you added to the acid is on the x-axis. So on the left, you didn't add any base, you just have acid. So the pH is obviously very acidic. As you add in a little bit more base, you get past, more. And eventually, that happens. Okay. There's 2 important points that you should know on this graph, on this titration curve, which is what it's called, okay? Titration curve has 2 important points. As this one, which is already labeled for you, it's called the equivalence point. The equivalence point, all titration curves will have this. Well, they'll have a slow increase, then they'll have a big spike, and then back to a slow increase. The equivalence point will always be in the middle of this big spike, in the middle of this vertical line. It'll always be directly in the middle here. Next, you also have the midpoint, which should be, this is the start and this is the equivalence point, should be halfway between the start and the equivalence point. So I'd say roughly about here. This would be the midpoint. And I'll show you a graph where it's labeled as well later. But for now, this is the midpoint. It's halfway between the start of the graph and the equivalence point. And the equivalence point I mentioned is halfway up on this vertical spike. Okay, so this is the midpoint, this is the equivalence point. Midpoint is also sometimes actually called the half equivalence point, which makes it easy to remember, but sometimes you may see it referred to as the midpoint as well. Okay. Now, what is the equivalence point? So the equivalence point is the point at which the acid and base have exactly neutralized each other and canceled each other out. So for example, if we had, and you guys have all seen this reaction before, HCl plus NaOH go into NaCl plus H2O, right? You combine HCl and NaOH and you just get salt and water. That's how the reaction works, and they neutralize completely. The equivalence point is always the point at which there's no more HCl, there's no more NaOH, there's only salt water, right? And that's because there's an exactly equal amount of HCl and NaOH. They're exactly equal. So because they're exactly equal and it's a 1-to-1 ratio, the reaction proceeds all the way to the right and all of the HCl is used up, all of the NaOH is used up. You just have salt water. If, for example, you go to the right of the equivalence point, you'll have slightly more NaOH than you will HCl. So all of the HCl will be used up to make salt and water, and most of the NaOH will be used up, but there will still be a little bit of NaOH left because it has nothing to react with, because all of the HCl has been used up. Because there's nothing left to react with, it's just left there, and it makes the solution more basic. That makes sense. So if you look at here, at this point, the amount of NaOH and HCl is exactly even. Starting from here to the right, there's more NaOH. Before this, there's more HCl. When you mix a strong acid and a strong base, like for example, HCl and NaOH, the equivalence point will always be 100% of the time at pH 7. So if you notice here, the equivalence point on the y-axis, it lines up with pH 7. Always with a strong acid and a strong base, it'll always be at 7. For when you mix a weak acid with a strong base, it's much more complicated and involves more math, which will not be asked on the MCAT because the MCAT is a multiple choice test and you only have a certain amount of time and no calculator. So they won't ask you the whole process because it gets complicated, it requires calculators usually, and takes a long time. So you probably won't be asked the whole process, but you may be asked parts of the process. So I'm going to go over some of the parts. Before I do that, I wanted to ask this. At about what pH is the equivalence point in this graph? And a lot of times they'll ask you questions exactly like this rather than having you figure out mathematically. They'll have you guesstimate based on a graph. Okay, I'm going to stop the poll. Yeah, and 100% of you guys picked D, which is the correct answer. Somebody actually asked a good question, which I was going to go over. This curve is backwards, or it starts off differently. The reason is because that last curve you saw, which is the one you'll probably see more often, it's when you start off with acid and you add in drops of base. In this graph, you start off with a solution of base and you're adding in drops of acid. You can tell because in that other graph, you started off with, when you hadn't added anything, you started off with a very low pH, which signifies you started off with an acid. In this, you start off with a base, which you can see because before you added anything else, it was very high pH, which means basic. And then as you added in drops of acid, it went down. The pH went down because it became, as you added acid, it neutralized and eventually became more acidic. Again, the difference is between strong and weak will be where the equivalence point is, where the midpoint is, all of that stuff. That's what makes the difference between strong and weak, both in acid and in base and whatever. And as for equivalence point, like I mentioned, this is where like the spike or the drop in this case is, and halfway through is about like here roughly, and that corresponds to about pH 6, right? And they won't give you like pH 7 or pH 6.5 or something like that as another option because they obviously know you're guessing, so they'll give you something easy like 1, 3, 10, okay? They won't give you anything complicated like that where it's like too hard to guess because, okay. Next, I do want to talk about how to do it mathematically slightly. So this is just really memorizing these formulas. So there's these couple formulas that I really want you to know. The first one is pKa equals negative log Ka, or pKb equals negative log Kb, but Ka and pKa are usually what we work with, so it essentially means the same thing. Before I continue, do very quickly want to talk about logs because when I've taught this lecture before, I noticed people kind of struggled with logs, and even in other lectures where we talk about logs. Logs are very simple. Logs are very easy if you just know how to do it. pK equals negative log Ka. So I'm just going to go over how to do a log real quick. log is the opposite operation of 10 to the power, right? It's the exact opposite operation. So for example, if you had 5x equals 25, and you wanted to find out what x was equal to, and it's 5 times x, you would do the opposite operation. So you divide both sides by you divide both sides by 5 because that's the opposite operation. You're multiplying by 5, so you want to divide by 5. And that's how you find out what x is equal to. Well, in here, you do exactly the same thing. Like I mentioned, the opposite operation of log is 10 to the power of. So for example, you could do 10 to the power of log Ka. So the opposite operation of both of these would be 10 to the power of 10 to the power of log Ka equals 10 to the power of pKa. Just like if you multiply something by 5 and divide it by 5, you can cancel out. If you take the log of something and 10 to the power of that, you can cancel out. So 10 log cancel out. All you're left with is 10 pKa equal to Ka, essentially. It's actually negative, but yeah. Yes, but I would call it something like an anti-log or inverse of log. Not sure if that's like an official term. But the official term I think is 10 to the power of. I'm not sure if anti-log is like the official term. And if there is something called an anti-log, I'm not sure what it is because I'm not really a mathematician. That might be like something involved in math or calculus that I don't know, and I don't want to give you a definitive answer because I just don't know. But yeah, 10 to the power of and log are inverse operations, just like multiplication and division are. Same thing actually with e to the power of and ln, right? If you do e to the power of ln x, again, they cancel out and you just get x. So if you did ln x equals y, and you wanted to find out what it was, e to the power of both sides. So again, e to the ln x cancels out, and you just have x is equal to e to the y power. Okay, and just like here, you have negative Ka is equal to 10 to the pK, but essentially it's like that. I'll give you an example. A Ka could be like 10 to the negative 7th. The pKa of this would very simply be 7, right? Because we talked about Ka is just 10 to that, right? So it'd just be like this. pK is just essentially the exponent of what Ka is, right? And it's negated because in Ka it's negative 7, and pK would be 7. Does that make sense? Does everybody understand how to do logs? Okay. This is more important. Kw is equal to Ka times Kb. And Kw is always equal to 10 to the negative 14th. This is like the constant of water, right? This is the constant of water, which is 10 to the negative 14th. And again, K times Kb. When you combine these two, multiply them together, you get 10 to the negative, 10 to the negative 14th. And this actually ties into this part, the pH and the POH, right? Because again, it goes to 14, but I'll cover that in a second. Next, Ka is actually also, you can relate Ka to concentration of H plus or Kb to concentration of OH minus. And it's just simply like this. So concentration of H plus times conjugate base over conjugate acid. Usually what they'll ask you to find, they'll give you a Ka, they'll give you the concentration of base and acid, they'll try and ask you to find this. So this is usually what you'll be solving for using this equation. Simply just memorize it. There's nothing else to really say. Just memorize it. KB is the same thing, except you're finding concentration of OH minus, and you're flipping conjugate acid or base. Very simple. And then you have here, which is pH equals negative log of concentration of acid. Again, it works exactly the same way as pKa and Ka. Concentration of acid is 10 to the negative 10. pH is 10. If the concentration of acid is 10 to the negative 3, pH is 3. That also tells you why lower pH is more acidic, higher pH is more basic, right? If you have a pH of 3, that means the concentration of H plus is 10 to the negative 3. Whereas if you have a pH of 11, H plus is 10 to the negative 11. 10 to the negative 11, and I'll actually write it out. 10 to the negative 11th is smaller than 10 to the negative 3, right? So a pH of 3 means this. So you actually have more H plus than if you had a pH of 11 overall. So that's what that means, right? And that's how that relates mathematically. But again, it's the same exact idea, but you may be given, like, say, something like a Ka value and asked to find the pH, and this is how you would do it. You would just find the concentration of H plus, and then from there you could find the pH. And again, just like with this, pH plus POH is always equal to 14, right? Because POH is just the concentration of negative OH. And you can, if you wanted to, I'm not going to go over it because it's just a lot of unnecessary writing, but you could actually just prove this using all of these formulas. You could actually prove this formula. But if you guys want to do it, I encourage you to do it on your own. If not, take my word for it. It does prove it if you cancel out. Otherwise, yeah, I would just honestly recommend memorizing this whole list of formulas. Some of these, like this one, and this one, even to an extent this one, very easy to remember or think about. So not really much effort required. These are a little bit harder. Those I recommend memorizing. But yeah, see if you can do this one fairly quickly. I'll give you guys like a minute or so for this one. So see if you can do it quick. So the majority of people pick answer choice B, and I would agree. I think it's B because, again, we have Ka of 1. And I'll just rewrite it 10 to the 0th power. That means pKa is 0, right? Because I just told you pKa is just the exponent. If you do 10 to the power of it, it's just the exponent. So pKa would be 0, actually would be negative. Oh, sorry, it would be negative 0, but which is also 0. So pKa is 0. I mentioned the lower the pKa, the more acidic it is. If you have a pKa of 0, that's fairly acidic. I mentioned you can't actually go below pKa of 0 in experimental real life conditions, but there are, like, HCl has a pKa lower than 0, has like -6. It's just because people like mathematically determined it. I think something similar to this actually, but I'm not exactly sure what Ka, like how to experimentally get Ka, but I'm sure there's a process and that's how they experimentally determined what pK of a negative strong acid is. But regardless, it would be pK would be 0, which is fairly acidic. So solution containing that would be less than 7. Okay, this is one of the last topics for today. I believe we have one more after this, but first I want to talk about what are multiprotic acids. So this is actually something we actually covered on earlier. H2SO4 goes into HSO4, goes into SO4. So most acids that we've talked about, like HCl, acetic acid, they have one H. They go straight from protonated to deprotonated. One H, that's it. Mainly, they have one protic event, but because they only have one H, but there are acids that are diprotic or triprotic, meaning that they can be deprotonated 2 or 3 times. Like for example, H2SO4 has 2 H's, can be actually deprotonated both times because it can lose both H's. This actually minus, this is 2 minus. So it can lose its H once and become HSO4. Then this HSO4 can actually lose its H again, become SO4 minus. Again, monoprotic HCl, sulfuric acid H2SO4 is diprotic, something like phosphoric acid H3PO4 is triprotic because you can go H2, H, and PO4. As for acid and bases, this is only an acid. This is both an acid and a base, right? Because H2PO4 can act as an acid and turn into HPO4 to this, or it can act as a base and turn back into this, right? So it can go both ways. And then again, HPO4 2 minus is also an acid and base. It can go back to H2SO4, or it can complete and become an acid and become PO4. And this is only a base. PO4 can't get more deprotonated. It can only go backwards to become, it can only act as a base and go backwards. Because even though they're both acids and bases, they don't have to be equally acids and bases. They can be stronger acids than they are bases, or stronger bases than they are acids. Not exactly sure with the numbers, and if they ever want you to know the numbers, they'll tell you. They won't really ask you to memorize it, so I wouldn't worry about it. But if you're curious, you can look it up, and it varies from, obviously, from molecule to molecule. So H2SO4 and HSO4 might be different than H2PO4 and HPO4. Okay, but that's the general idea. Things can get deprotonated multiple times, and the way you would know that is if it has multiple H's on it, right? That can dissociate. So for example, like something like acetic acid, which has the formula CH3COOH. Technically, it does have multiple H's, right? Right here it has 3 H's, but these are not acidic H's. They can't actually come off. So it actually, it won't count as like a quadprotic or whatever, or multiprotic acid, because it can't, these H's can't come off. Only this H can come off. And the way you would know that is if it's attached to a carbon, it most likely can't come off. If an H is attached to a carbon, it most likely can't come off. It's very rare that it can act as an acid if it's attached to a carbon directly. And that's because the pK of those hydrogens specifically would be like, I don't know, like 50 or something, and it would be really, really, really hard to get them off. Now I want to talk about multiprotic acids titration curves. So this could be the titration curve of a diprotic acid, right? Because it has 2 equivalents, because it has 2 deprotonation events. So for example, this is probably H2SO4 or something similar, something that's diprotic. Again, starts off in H2SO4, then slowly it gets turned into neutralized, and at about this point, or somewhere roughly there, there's no more H2SO4. There is pretty much only HSO4 at this point. Pretty much all of the H2SO4 has been converted into HS4 by this point. Then HSO4 keeps going, and then at about, say, at this point, it's HSO4. At this point, it's about only SO4 minus, 2 minus. This is minus, right? Next, I want to talk about these points, right? We talk about titration curves has 2 important points. We talk about the equivalence point, and notice how here the equivalence point is less than 7 because it's not strong acid and strong base, right? Not exactly, but otherwise, we talk about this, the midpoint, which is halfway between the start and the equivalence point, right? And if we consider like this the start and this the next equivalence point, so the second midpoint would be here. The midpoint is when the concentration of acid and conjugate base are equal, right? With the equivalence point, it's considering the acid with the amount of base total, right? With the base you're adding. However, with the midpoint, it's more talking about itself. So we know that at the start, it's H2SO4 only at this start. At this endpoint right here, it's only HSO4. So as you rode this line, all of the H2SO4 would have slowly gotten converted like one atom at a time, essentially, into HSO4. At this point, the midpoint, 1, the amount of H2SO4 and the amount of HSO4 are equal. So what that means is, at that point, exactly 1/2 of the original H2SO4 has already been converted. The other half is yet to be converted. It hasn't changed yet, but it will be if you keep adding more base. But at the midpoint, exactly 1/2 has already been changed into its alternate form, right? And again, in this midpoint, it would be half of HSO4 has been converted to just SO4, right? So the concentration of, at this point, concentration of HSO4 and SO4 are equal, okay? This question, I'm actually just gonna skip this question. I'll give you guys like 2 seconds to think about it just by looking at it. But I will slowly start to go over it because just we don't have enough time. If you consider the titration curve in which an acid is treated with a base, so again, titration, acid base is monoprotic, so it's only one H. Which defined compounds could be the acid that's being titrated? Well, this involves a lot of your knowledge that we talked about today. Again, it only has one curve, so it's monoprotic, right? It only has one protonation event. If it was diprotic or triprotic, it would look something like this, right? Or if it was triprotic, it would look like more like this, right? It would have multiple curves. But since it's one curve, you know, it can't be H2SO4, which is diprotic. The others it can be because the others are monoprotic. Next, you would look at the equivalence point. So the equivalence point would be somewhere here, maybe, right? Somewhere like roughly around there. So that's about, I would say 9. Remember that I said that if you add a strong acid and a strong base for titration, the equivalence point is always at pH 7. In this case, it's pH 9. They told you that they're adding in a strong base, NaOH. So that means if this was a strong acid that they were adding in, the equivalence point would be at 7. Since it's at 9, it can't be a strong acid. It has to be a weak acid. HCl is out because HCl is a strong acid, right? And we knew that based on the equivalence point. Lastly, and I guess I slightly didn't cover it, but you could have made the leap. When I said that for the midpoint, which is, I would say about here, which is equal to pH 5, which is equal to pH 5. The midpoint is when exactly 1/2 of the conjugate base has turned into acid. We've actually seen that before, where the conjugate base and the conjugate acid are equal. We saw that in the Henderson-Hasselbalch equation. Remember, where it had log base over acid, right? And when base over acid were equal, that's when the pH equals the pKa. When this happens, when they're equal, pH equals pKa, if you guys remember that from earlier, right? What that means is, since the midpoint is the point at which the pH and the pKa are equal, and we know that the pH is equal to 5 at the midpoint, the pKa of this solution must be 5 as well. That's because at the midpoint, the pH is equal to the pKa. pH we know is 5. We know 5, we can substitute in 5 equals pKa, pKa equals 5. they give us the Ka values, right? Of all of these. We know the conversion rates of Ka to pKa. This has a Ka of maybe 5-ish. It's not exact because you're multiplying by 1.5, but 1.8, but it's about 5. This would be maybe 4.5, and this would be 10.5, something like that. Since they gave us the Ka value, we know that the pKa's are 5, 4.5, and 10.5 of these three respectively. We're looking for a pKa of 5. Out of these, this one is the closest. So I would say the answer is C. Because the Ka, from the Ka, you can find a pKa. The pKa, you know, has to be 5. This was the closest one that's 5. 4.5 is close, but 4.5, if you look at the graph, 4.5 would be somewhere right here, which is definitely not in the midpoint, right? Even though 4.5 and 5 are close, and I said they usually won't give you something close, they're asking you to estimate, they made it easy enough to differentiate because 5 is over here, right? You can draw the line. 4.5 would be somewhere like right here, which is very clearly like far away from the midpoint, right? It's very far away. So that's why I would say the answer would be C.